One of the most important application of the observational parameters of binary star systems is the mass-luminosity relation. And from this mass-luminosity relation, we have actually gained enormous insight into the stellar properties of the stars. And as we keep on repeating that all our knowledge is gained by iterative application of the previously gained knowledge, right? So, once we had enough number of binary stars whose properties had been observed, that is when Eddington, the great theoretician, he used the data of these binary stars to get a relation between the masses of these stars and their absolute luminosity. Now understand, this absolute luminosity requires a knowledge of the distance to the star, right? Now it might happen that you can measure the distance of one of the components of the binary, then immediately you know the component of the other component of the binary star, right? Now what happens is that although the binary stars are moving around each other, so their distance with respect to our point of observation is changing, that change is negligible. And we assume that the two stars are always at the same distance from us. Now, once we know the distance and we measure the flux, or we can estimate the flux from the other star, then we know the luminosity. And once we know the luminosity, and at the same time if we measure the spectrum, then we know where the star can be put in the HR diagram. And this is exactly how the initial phases of the HR diagram was actually plotted. Hertzsprung and Russell independently used many different kinds of observations, many different methods of physical estimation of the luminosity and the spectrum, and the corresponding temperature was measured by observers later. Okay, so now this is a very, very interesting plot which tells you that this whole method is an iterative process. What we mean is that you obtain the estimate of mass, you put it back in the database, you go and redo the calculation, and you obtain a better estimate of the parameters. And this shows that for different masses, in the y-axis here, we are plotting the mass in the log scale, and this is the luminosity, which we are plotting as absolute magnitude. Okay? So now, if you look at it, it is not a straight line. So when we talk about the mass-luminosity relation, different masses actually have a different relation with the luminosity. And this quantity is actually very empirical. When we say empirical, what we mean is that we can fit a mathematical formula to a certain range, but we do not know the physics behind it. So the triumph of theoretical physics in explaining the stellar properties is that you should be able to predict observed properties that you see out here. So what you see as a mathematical property is that the luminosity is proportional to mass, okay, and you will write mathematically L is proportional to m raised to an index A, where of course L is given in terms of the solar luminosity and mass is measured in terms of the solar mass. Now, if you look at this particular data set, then you see the luminosity here is in the y-axis, the mass is in the x-axis. It is just opposite of the previous picture that we had, right? So we can actually plot them differently depending on how you want to interpret the result and develop a model for it. Okay? And as it happens, sun typically always appears in the middle of the whole stellar properties. Whether it's in a HR diagram also, it appears in the center point. And when it comes to the other properties like mass-luminosity relation, there also it has to appear in the center point because the mass is kind of a center and the luminosity also is kind of a center point. Okay. So this is also a particular relation that can be had. Now, if we look at the HR diagram out here, this is your luminosity and this is the surface temperature, this is where the sun is. So you should be able to move from this picture to this picture and vice versa. Spend some time on it. Think about it, how we are looking at the luminosity, okay, both on the y-axis, and see how this is my temperature is plotted in the HR diagram, and temperature here is plotted with increasing towards the left. Okay, here we are looking at the mass which is increasing towards the right. Okay, so that should give you a very good picture of how your mass is related to the luminosity and the temperature, and the temperature is also classified as the spectral classifications. Okay, so you should be able to navigate the picture from this diagram to this diagram and vice versa. Okay, now modern day understanding tells that when we are talking about this particular quantity A, then these are different values and the coefficient of this proportionality is also different when we are talking about different ranges of mass. So, if we are talking about very highly massive star, okay, so OBA, those kind of stars, okay, so basically we are talking about O star, where the mass is greater than 55 solar masses. That is when you have your luminosity is linearly proportional to the mass. Okay, of course, this is your coefficient. Then, for a great range of mass, and this was the range up till your F type of stars normally. Okay, here we see that the proportional constant is 1.4 and the index A is 3.5. As we go to the lower classification of stars, where we are talking about stars which are similar to the sun, okay, then the index A is slightly higher than the index out here. It is of the order of 4. And the funny thing is, as you are moving from higher massive stars to lower massive stars, the index A is increasing. But as you go beyond this threshold, the index decreases. It becomes 2.3. And of course, the proportionality is now 0.23. Okay. So, this change has to be explained by the stellar theory, which is actually beyond the scope of these videos, but understand it's a very, very complicated system, perhaps the most complicated system that we can think of in the universe. That a whole star system where all the laws of physics that we have learned is applied. So, huge amount of simulation is required to predict the theory and the theory's outcomes. Okay, so the explanation of these is actually a cutting edge problem, research problem for theoretical stellar physicists. Okay, now as we said, these are empirical observations and these are observations and empirical fit to the data. Now there are multiple ways you can fit the data. So another way is that when it comes to the K-type main sequence stars, so you're looking at stars which are 0.2 solar mass and 0.85 solar mass. This actually overlaps these two regions. Okay, so when you have these two regions, then you can write the luminosity is proportional to the mass where A is no longer a constant like here, but it is a function of the mass out here. And if you take this formula and this formula, then you'll realize that here, although it is discontinuous system, but this is a very, very continuous mathematical function. And that is why theoreticians prefer this kind of a formulation, because it's easier to fit mathematically. Okay, because it's a continuous system that fits the data in these two different classifications.